Nice. All right. Hello, everyone. Accidentally turned on and off the projectors 3 times, so they'll turn on eventually. So that'll eventually work out. But howdy. Reminder to y'all, logistics-wise, quiz 2 due this Saturday. Also, this first professional development activity. There's 3 of them. The first one on just like identifying what you don't know. That's open. So remember, that's either looking for a job posting and finding some skills it requires that you don't have, or the NACE competencies and things like that. And the motivation here is you don't know what you don't know. And looking through this, my hope then is you'll identify that, hey, I may not learn these skills in my classes, but maybe if I look outside my classes, I can. And that's the dream. So we'll see. That's the end goal with this, and to get you all involved in those things sooner than later. Too many people wait. So, eventually, maybe they'll turn on. We'll do the joke while that's going on.
All right. Okay. And that works. Perfect. As a planetary scientist, I really like this one. So, I love the way the Earth rotates. It really makes my day.
Oh, I did it last time. You weren't here for it. But you all remembered, so that's special.
Okay. If you've seen one indoor shopping center, you've seen them all.
You've seen a mall? Seen them all? Seen a mall? It's good. All right. So, last week we did Gauss's law, and so a couple of points is, so I've had some people attend my office hours, which is awesome, and I want to remind you all that my office hours, the way they're designed, is it's a big old tape, well, relatively big. I can fit like 9 people in my office, and there's a whiteboard table and a whiteboard on the wall, and there's snacks and all that. The whole point is to practice problems in it. That's the reason it exists. Come and ask me problems, and there's places to actually practice it. So it's not like a traditional kind of office where I sit behind a desk, you sit on the other side in a chair and have your stuff in your lap. No, it's like a table and it's great. Why do I mention this? I've had a few students come in, and this is super useful for me because it helps me identify the areas that people are running into challenges for. And so to that end, I made 3 extra slides on the last PowerPoint, which are not showing up. Oh, yep, there they are. All right, so 3 extra slides. They should be on there, so they're the Gauss's law, and they're for 3 different purposes. So I'll start with this one first. So the really common challenge people were running into was setting up Coulomb's law integrals. That was one of the most common challenges that people were running into, which is not unexpected. But it was good for me to see that, and also when I was working with students, there is very much a recipe when it comes to doing these problems. There is a process. And we practice this process, but here I've made that process explicit. So what do? First, you draw a picture. Always draw a picture. Draw a picture with known variables labeled, and you kind of like pick a DQ on it. So let's like look at that line of charge. So you have a line of charge. We have the point we care about, and we'll pick like a little DQ, a little tiny bit of charge. And then maybe the problem says it's a distance y above it, and we'll draw a distance r here. R is the distance from the charge to the point we care about. So we draw our beautiful picture with the things that we know. Then we start with this integral that I wrote up there. E equals the integral of k dq over r squared. First step is we need to change that dq into spatial coordinates. We talked about that. How do you do that? You multiply by the charge density. And in all the problems I'm going to give you all, they're all going to be one-dimensional problems. The reason being is I can't, because Calc 3 is not a prereq for this course, I can't assume that you know how to do double or triple integrals. So all that to say, we have to work in one dimension, one integral. So all of them are basically going to be a line of charge, whether that line is finite or infinite, that varies. Whether or not it's a loop or whether or not it's a straight wire, that varies. But in all cases, a loop of wire is still one-dimensional. It just wraps on itself. So we set dq equal to lambda dl. Remember, that comes from the definition of lambda. Lambda is charge over length. Therefore, if you kind of rearrange this and take the derivatives, you get dq equals lambda dl. Awesome. Now we're going to get dl in terms of a Cartesian or a spherical coordinate. Depends. If my wire goes left, right, we're going to probably use dx, because to integrate over the length of it, if it runs left-right, x is what goes left-right. If it goes up-down, then we'll use dy instead. If it makes a circle, then arc length makes the most sense, such that we integrate over the whole line. Whether or not we're integrating left-right, up-down, or in a circle, these are kind of the options. Now, great, you got this integral in terms of k, lambda, and d, some spatial coordinate. You then need to break into x and y. How I've taught you all how to do that is by doing this angle. You add an angle to your picture, and then you kind of do what you've been doing up to this point as far as components are concerned. So this little dq would make an electric field that points like up to the right if it was positive. We draw how would you break this into components? Well, it sure would be nice if I knew this angle phi. The reason we're using phi is, if you notice here, theta is used for something else. So we're going to use a different letter because if you have done the circle of charge, there's one problem I've given you all where it's a half circle. If you started that, you'll realize you need two different angles. Actually, that one's the same angle. If you did the circle of charge, there's two different angles. The one we did in class. So whatever, we're going to call it phi. And then if you want that component, in this case, cosine of phi, sine of phi, and then I want to point this out. Direction matters. If all components point to the left, then you should put a negative sign in front of your integral. If all the y components point up, then you should put a positive sign. If all the y components point down, then a negative sign. That's going to come. The question on the quiz that's due this Friday or this Saturday is a line of charge. Find the electric field at some point P above the leftmost end. And you'll notice that the answer, I'll either ask you, depending on which version of the problem you'll get, it'll either say, give me the integral for the x component or give me the integral for the y component. You'll notice that the answers have positives and negatives in front of them. Why? Because if all my x components point to the left, then I should have a negative sign. If all my y components point down, I should have a negative sign. If all my x components point to the right, I should have a positive. If all my y components point up, I should have a positive. So that's something to keep in mind. I kind of tossed that in this quiz to see if you're remembering that left is negative and down is negative. And the last step, get everything in terms of known variables, and then you would integrate. On the quiz, it just says, what is the integral? I'm not as worried about solving it because that's math, and it takes longer than I really want you to spend on it. So, anywho, recipe. If you're like, what? None of this makes sense? Start trying the problems using this. Start trying the problem. Once you kind of start trying the problems, you're going to see that this is the process. This is the process I used when I solved them in class. Try them for yourself, and as you're doing so, you'll realize these are the steps that you're doing. If you get stumped, you can refer to this to figure out the next step. So, there's that. This is based on a handful of people that came to my office that all had the same questions about this, and me realizing when I'm helping people with this, I am just having them go through these steps. So, make them explicit for y'all. All right. The other thing, I made a couple more slides in here. One is, when should you use Gauss's law? Because now we have two techniques to find electric field. One is doing this integral with coulombs. The other is Gauss's law. Rule of thumb, use Gauss's law if possible. Why? Because it's so much easier. Finding the electric field using Gauss's law, you don't have to do an integral. You can actually get the electric field. So, use Gauss's law if possible. When can you use Gauss's law? When either your Gaussian surface is such that the E dot dA is 0 or the E dot dA equals E times A. What situations does that happen for? An infinite rod or line with a uniform charge density, an infinite plane with a uniform charge density, or some combination of spheres / hollow spheres. And we did a couple examples last class of those. Those are the three scenarios you can use it for. If it fits within one of those criteria, you can use Gauss's law. You cannot use Gauss's law for a finite length rod. It has to be infinite due to symmetry to make all these things work. All right. And then the last thing I'll show you all is I then made a step-by-step on kind of a guide for how to do Gauss's law. We practiced some last class, but just to make it explicit, the steps that we did. So you start with Gauss's law. First you draw a picture. You always draw a picture. Draw a picture with what's going on in your picture. Draw a picture with the Gaussian shape around it. What Gaussian shape do we use? There's a nice little slide in here that shows that. For a line of charge, you do a cylinder around it. For a plane of charge, so it's this picture here. These dotted lines are the different Gaussian shapes. For a line of charge, it's a cylinder around it. For a plane of charge, it's a cylinder going through it. For a sphere of charge, it's a sphere going around it where these objects intersect the point that you're trying to find the field at. Notice that point P lies on the surface of each of these at different places. Cool? So that's a reminder there. You have your integral here. Gauss's law is left side equals right side. Integral of E dot dA equals Q enclosed over epsilon naught. So we just do one side at a time. To solve for E dot dA, there's three scenarios. If you have the line, it's going to be E times the area of the rounded side of the cylinder. You can go back to picture and we chat about why. If it's a plane, it's going to be E times the area of the two sides of the cylinder, two flat sides, the top and bottom. If it's a sphere, it's going to be E times the area of a sphere. That's just kind of what all this boils down to. You'll see when you look through these problems that this is pretty much what they always boil down to. Great. Left side's done. Left side's easy, generally. The right side is where things might get a little bit trickier. If the charge is completely enclosed, then just put that as the charge enclosed. So to give you an example of that, we did the sphere last class. And so we found the electric field at three different points. Sorry, these PowerPoints are actually from low cost at top, but whatever, it gets the point across. We did three different points. Point A was inside it, point B. So I have a hollow sphere, and I want to find the electric field at three different locations. The first location is inside the empty space of the hollow sphere. The second point is inside the shell of that sphere. My third point is outside the shell of that sphere. So, inside of it, when I draw my Gaussian sphere, there is no charge enclosed. So the electric field is zero because there's no charge enclosed, so the right side is zero, and that's the answer to the part A here is zero. When you then do part C, and you're finding the electric field on the outside of it, how much, I draw my Gaussian shape, how much charge is enclosed by that sphere? All of it. What is all of it? Just Q. So boom, you just put Q there, rearrange, easy peasy. Then we did the crazy part, where if you're inside of it, this is the one we actually worked on last class. What happens if you're inside of it? If you don't enclose all of it or none of it, you're somewhere in between. So this is written out here. If you're somewhere in between, you find the charge density, and then you multiply by the amount enclosed, by the volume enclosed. All right, so that's what we practiced doing last time. That was the step we do. If you remember last class, that was the trick I told you. Find the charge density, then you take that and you plug it back in to find the charge enclosed. That was the last problem we did. So, try these ones out. But I've made these slides, which hopefully should be uploaded now. I'll double check later in class if they're not. And these are kind of help you out with these because I know these are some of the trickier things. And at the end of the day, they are fairly formulaic. There is a process. All of physics is about can you do the process. And yeah, anyway. So there you go. That's to hopefully help you all out. We'll see how it goes. Make sure you are trying these things because, yeah, as I told you all, the beginning of the semester is the hardest part, in my opinion. Kind of peters out as time goes on. All right, so to today, what are we going to do today? We're talking about electric potential. Oh, that's why I was in the wrong folder. I was so confused. All right, so today, Gauss's law is a bunch of math. It's a math trick that lets us solve things that otherwise would be impossible without a computer. Now we're going to get back to discovering new physics. So now we did our little math trick, let us solve some things we otherwise couldn't solve. Now we're going to kind of keep building our knowledge. So if you'll remember, I told you everything we learn is based on observations of reality, and then we build. We build on top of each other. And so that's the cool, as a physics major, the cool thing is throughout your classes, everything builds on something before it. You never skip stuff. As engineering majors, computer science, you all will just by nature have to skip stuff because to actually learn where some of the equations come from in your future classes, you have to get a PhD in the field. And that's way more than you need to do to be able to do it. Sometimes it is useful to just say, hey, here's the equation for it. If you want to learn where it comes from, spend a lot of time on it on your own time. But in physics, everything builds. So, next step is electric potential. This is something you have heard about before, guaranteed. And if you're like, I haven't heard of this phrase before, If I put the letter for it, then you're definitely going to recognize it. The symbol for electric potential is V. It's voltage. So voltage is something hopefully every single one of you has heard at some point in your life. Every single electronic device you possibly have is going to have some little tiny print on it. Your phone doesn't say it, but almost everything, like my little battery charger here has a little thing that says voltage and all that stuff. Almost every electronic device has this written somewhere on it. Batteries, great, you've seen it on there. I'm going to teach you what it is. It's and it's incredibly useful, and it's something that at least 95% of people out there have no idea what it is other than it's written on their batteries. That's the most extent. And they know that bigger batteries have a bigger V, but that's not actually always true. So even that's not even accurate. A D cell, those big fat ones, and then like the AA and the AAA, they're all 1.5 volts. So what's different about them? Good question. We can chat about it later. Maybe at some point. But that's what we're going to cover in this PowerPoint. Super, 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 super useful. But we're going to build to get there. We're not going to start with electric potential. We're actually going to start with some things from Physics 1 and then work towards potential. Doesn't just come out of thin air. So we're going to derive it in electric potential energy. We're going to identify what they are, how they're useful. It's going to be great. So first thing, from Physics 1. See if y'all remember how to do this problem. Because the concepts that there's two ways to solve this. There's one specific way that it'd be cool if you used, if not, whatever. As long as you'll notice, we'll see which one you all use. From Physics 2048, you drop a water balloon with mass 1 kilogram to the top of the physical science building. It's 10 meters high from the ground. How fast is the balloon going right before it hits the ground? See if you all remember how to do this. And my hope with y'all is that you remember how to solve this with energy. I'll give y'all a hint. My dream is that you all remember how to solve this with energy. If you use kinematics, that's fine. But really what I want to see is energy. But if you do kinematics, that's fine. It just won't connect as well. We're going to solve this with energy. That's the concept you need to remember.
I don't know the reason. I did MGH and medical
I think you're also going. You said it equal to 100.
Yeah. So I did the times 2.
Because I got 14 at the end reference. Maybe you're right.
Did you do that from there?
Not right. Yeah, I got 14. But
Well, that makes more sense considering it's I didn't write out.
I don't know.
Yeah, and that's what
you know what it is? You're putting pounds on a. Yeah, and that's just the square root of that. It should be 14. Because it's 196, and then that's a perfect square root of 14.
No.
Oh yeah, that'd be interesting.
Yeah, that's
Yeah, the other one you probably do it. That's why I also did MGH.
Maybe you can accept that.
Oh, that's and then fresh under at like 30 miles per hour.
All right, I'll give y'all like 20 more seconds. If you remember, great. If not, take your best shot. All right, we'll close this out in 5, 4, 3, 2, 1. All right, so there's only 2 answers that are kind of reasonable. That's always important to think about. There's only 2 answers that are reasonable. It's the ones in the middle. 196 meters per second is like stupid fast. A really good metric for you all to remember. I just find this useful. I don't know. You are going to be in the kind of in-between zone as whether metric and US, so it's good to be able to convert. 27 meters per second is about 60 miles per hour. It's a nice kind of like touch base of how fast meters per second is. So yeah, we're not going hundreds of miles per hour. 5 meters per second is then pretty slow. So it's not going to be that. It's always good to kind of like think about what makes sense. But yeah, this one's going to be conservation of energy. That's at least the connection. I should have made you required to be used conservation of energy. If instead I'd made this like something rolls down a hill and it starts 10 meters high, and how fast is it going at the bottom? You can't do kinematics with that if I make the hill all bumpy and things like that. That's why energy is so awesome, is that you can solve problems that with kinematics wouldn't be possible. So, recap. Energy I start with plus work equals energy I end with. This is kind of conservation of energy. Whatever I start with plus work. Work is just whether or not you add energy to a system or take away energy from a system. That's the way to think about work. If it's positive work, your final energy is bigger. If it's negative work, your final energy is lower. In this case, we're going to assume that there's no air resistance or anything like that. So that's going to slow things down and steal energy. At the beginning, there's no kinetic. And then at the end, we are going to set the ground to 0. You don't have to, but it makes our life easier to set the bottom as 0. So that makes our potential at the end 0. And so we get mg, and I like to use y instead of h to stress that it's based on where you're located. Height is kind of like a weird, it's not as clear. And great, you solve this, the m's cancel, so vf equals the square root of 2gy, and that comes out to 14. Yay, conservation of energy. So basically this was, if you did kinematics, that's solid, but I want to make sure you all remember conservation of energy, because we're going to use it. It's going to come up in the next few slides to help us understand this gravitation, this electric potential. All right, continuing to lean on things that you learned in the past. From your Physics 1 class, what quantity is determined by taking the dot product of force and displacement? Is it, you know what, I'll even, no, I'm not going to write it. It's technically an integral. Is it the spring constant? Is it displacement, acceleration, or work? I'm going to give you all 30 more seconds. Yeah, so that's going to be the rest of it. Yeah. All right, in 5, 4, 3, 2, 1. Don't forget to click the buttons, all that good stuff. All right, so this is just a definition. It is what it is. What is the quantity that we call the integral of f dot dl? It's work. Yeah, there it is. So it's work. What is work? It's how much energy you're adding or taking from the system. That's the way I kind of describe it. If you're applying a force in the direction you're moving, you're going to get faster. Therefore, you're adding energy to the system. If you apply a force that's opposite the direction you're going, you're taking away energy. You're slowing it down. So this is going to come up when we derive our stuff today. Because guess what? We've learned about a new force that we can chuck in this equation and find things. So you can maybe start to see the foreshadowing. We've learned an equation for force between two charges. And if I plug it in here, I can find the work done in the inner. And so just to give us the next slide, there's two equations you all need to remember. Work is the integral of F dot dr. It could be dr, dl, dx, dy. It's just the direction you're moving. And the other one is that work is equal to the negative change in potential energy. Work is equal to the negative change in potential energy. That relationship comes from finding the work done by gravity. And when you do the work done by gravity and you drop, and something goes down, you find that there's this negative sign that gets kicked out. If you wanted to derive that, you would just literally find the force of gravity, which is m times g. And then you would do from a high point to a low point, and you would see that work does there's positive work when you're falling, but it equals this negative change of potential. Whatever. Definition from Physics 1. I won't get too much into it, but it's something we're going to use. If work equals negative change of potential, and work equals the integral of f dr, then they equal each other. If A equals B and B equals C, then A equals C. Then they equal each other. So, just to write that out, that means that the negative change in potential is the integral of f dot dr. If A equals B, B equals C, they equal each other. That's the logic here. We're going to use that to find the energy stored in a system of two charges. To find the energy stored in a system of two charges. A system of two charges can do work. How do you know that they can do work? If you have two positive charges, what are they going to do when you let them go? Repel. They're going to start moving. There's going to be a force, and there's motion, and you can do stuff with that motion. Work is all about just gaining energy. When they're stuck there, think of like a rubber band. If I stretch a rubber band, it has energy stored in it. How do I know that? When I let it go, it does something. Potential energy is just energy stored such that when you release it, something happens. It gets released as kinetic, generally. Not always, there's caveats, but okay. So, real quick, let's plug in, there's something else we learned, and it's going to show up in the next slide. Remember, y'all, that E equals F over Q? That's the definition of the electric field. Rearrange that. Therefore, F equals E times Q. I can then take this, and I can put it right here. And so we get that the change of potential equals the integral of E times Q dot the direction I'm kind of moving. So that's what's on the next slide. It's on the next slide, a little prettier. But I wanted to show you where it came from as opposed to just shoving it up here, then you'd be like, what? So change of potential equals work done. Negative work done, just move the negative side to the other side. Replace F with E times Q. Q is a constant. Pull it out. Yay. Yeah, we're building. We're taking prior knowledge and connecting pieces to discover new things, to derive new expressions. So the next step is we're going to find the energy stored in a system of two charges. How are we going to do that? Q is going to be one of the charges. E is going to be the electric field made by the other charge. We're going to plug those in and do an integral. It's going to be pretty easy integral. So, let's try it out. So we got 2-point charges. Q1, Q2. One's located at the origin, the other's at some distance xi. How much work is done, i.e., how much energy do I store or release if I move the charge from Q1, Qi to Qf? As always, we draw a beautiful picture. Here's my charge. Whether it's positive or negative doesn't matter. We're going to pretend like it's positive, but it won't really matter. Q1 goes there. Q2 goes at some random spot, some distance xi away. And the question is, how much work is done if I then move this charge to some hypothetical location xf that is, it could be closer, it could be farther, it doesn't matter. We're just deriving this expression. All right. So, what are we solving for? How much work must be done? And we have the expression on the last slide. Remember, y'all, work equals negative change of potential energy equals the integral of Q E dot. Now, which normally I'd put like dr or dl, but let's change that into coordinates I care about. Which way is my thing moving? Up, down, left, right? To the right, left, right. What variable do we like to use for left, right? So let's instead write dx, the direction of motion. All right. I'll do one last step and then leave you all to do it. Our bounds are xi to xf. There is bounds to this integral. So last question to y'all is, what's the equation for the electric field? So Q2 is the one getting moved. Q1 is the one making the field. What is the equation for the electric field due to a point charge? K Q over R squared. All right. There you go. Go ahead and try to do that integral. You might have to change some variables to other names. You're allowed.
Yeah, it's easy. The part is, let's see if people want to do x right. There you go. Yeah, that's the key. That's super easy.
So can we integrate that as this demonstration? Well, what's our constants? Okay, we pull that out. Q is also a constant. Yeah. What about that R? What's up with that?
Just change that.
Change your next video. Yep, that's it.
And then
You just have to realize that R is just the distance between them.
Equal K out. It doesn't bring up
I mean, the other
Like R
expression
max Q.
right. It's gonna
You
be
really
it's gonna be 1 over
Q
x squared.
is the square root of x squared is y squared.
And that's the
this A was
Q2.
okay. Wait, up here too.
That one's Q1, and then one on the outside is Q2. So you need to so you'll have
So this formula here, what Q is this?
that's Q2. Yeah. So one outside there.
And this is
Q2 is the one inside is Q1.
Don't figure out how to make the integral actually doable.
You can pull up K and pull up
So, what's constant? Great, pull it out. Hell yeah. Do what left over. Dx over R squared. Is R constant? What is R represent?
-1. No, because we're adding.
The distance between one and one.
Well, what's it?
This is one charges. Have we been labeling that as R this entire time? What are we labeling that as?
-1.
What's that?
I'm thinking it's 3.
R is what?
Yes.
R represents the distance between them. How do we actually do one? That makes sense.
when you put it in variables.
And that's bad.
Crazy pronoun because
Q is acted on by a force.
over the distance. Yeah.
And this is G squared.
Over the distance including the field made by Q1. And to the integral of the field made by Q1 over the distance Q2 travels. Which is why the downs are x half and x half Q1, Q2.
All right, so the key here is realizing that r is the distance between them. So what can I replace it with? What variable have we been using for the distance between them? X. Replace it with x, and then you just integrate. So realizing you need to substitute variables in here. We don't, r, what? Replace it with a variable we do know. R is the same as x in this problem. It's the exact same thing. So pull out your constants, and then it's just the integral of xi, x final, of 1 over, well, dx over x squared. Super, super easy integral. It's x to the minus 2, becomes just 1 over x, but you get a negative sign that gets kicked out, so you get negative k q2 q1 times 1 over xf minus 1 over xi. Boom. All right. Now, to get to the next slide, I have a follow-up question for you all. To get the energy stored in this system, so right now it looks a little messy. It's a little bit like there's a lot going on here. If I want to get the energy stored in the system, it'd be helpful if I started at a place where there was zero, so this is the difference in energy. If you all remember, work is the change in potential energy. So I have some energy I start with, some energy I end with. If I wanted to start at 0, such that however much it changed is just the energy I have. So long story short, my question to you all is, where can I start? Where can I make my xi, my initial position of charge 2, such that 1 over xi disappears, turns to 0? Where could I start my charge such that where it initially is located, that term turns to 0, that 1 over xi? So let's try some. So someone mentioned the origin. If I start at the origin, that would be 0. What is 1 divided by 0? Undefined. So that one's not going to work for us.
Infinitely far away.
We do infinitely far away. If I divide 1 by an infinitely large number, what does it turn into? 0. So, all of this is building towards finding the energy of a two-charge system. If I start at this equals infinity, what ends up happening is my work equals negative, and actually let me remind you, my work equals my negative change in potential equals my negative k q2 q1 over my final location. So long story short, my change in energy is k q1 q2 over the distance between them. Ta-da! We just derived the energy stored in a two-charge system. If I take one charge and place it somewhere, that's free. Nothing's fighting it. I can place one charge in the middle of nowhere, no problem. Nothing is fighting it. You want to bring a second charge in, you're either going to have to fight that field to make it happen, thereby storing energy. So, this just has that in writing. So this down here is the energy of a two-charge system. Take one charge, place it there. That's free. Second charge has to fight the electron. If you have two positives, that's the example I keep mentioning to you all. If I had a positive charge, boom, free. If I want to take a positive charge and then bring it all the way into here, I'm going to store energy. How much energy? K, Q1, Q2 over R. That's how much energy is stored if you have two charges there. And if you let those charges go, that energy will be released. You all may or may not have seen a similar equation like this for gravity. The energy stored between two masses is going to be G m1 m2 over R. If you have two masses and you bring them near each other, how much energy is kind of stored in that system? It's the same thing, but with m's and a G instead of a K. So, we have derived the energy stored in the system. If you're like, why are we doing this? Why are we suffering through this and finding energy? Energy is incredibly useful. It explains everything in the universe with one simple statement. Everything wants to go to lower energy. That statement alone can kind of explain almost any interaction that kind of happens. You might have to jump through some hoops to kind of like make it sense for most things. Why does the ball drop? Because it's going to lower energy. Why does the spring get released? Because it wants to go to lower energy. Why do two charges move away from each other? Two positive charges? Because it's going to make this energy less. It's another way of viewing the universe, and the beautiful thing about it, it's a scalar, so you don't have to do vector stuff. And when we get to electric, and it doesn't matter the path you take. It's something else we're going to learn. The energy release doesn't matter about the path you take, which is super handy. Physics 1, you all did some stuff with conservation of energy. It's so nice. It's so useful. There's a reason when you all work with batteries, they must... I do want to make a very, very important here. We haven't gotten to voltage yet. Electric potential energy is not electric potential. It's got an extra word. Sounds stupid, but they are going to be different, and you are going to mix them up. We haven't gotten to voltage yet. We will. We will definitely get to voltage in today's class, but we haven't gotten there yet. And we'll do some problems with voltage, and it's going to be great. It's going to be so much easier than other stuff you've done. All right. So let's just, play around with this equation, see if it makes sense. I have two charges, both positive. What happens to my energy stored in that system if I double the distance between them? Do I get double the energy, half the energy, the same energy, or 1/4 the original energy? What do y'all think? All right, 10 more seconds. In 5, 4, 3, 2, 1. So you got two charges, boom, one charge, and the question is, what happens to the energy if I make them twice as far apart? Remember, this idea of potential is energy stored that can then be changed into something. We can immediately see if they're closer, more stuff is going to happen. They're going to be pushed stronger. That means you can get more energy out of it. How do we see that mathematically? The energy stored between two charges is KQ1, Q2 over R. Remember the strat for this, y'all, is you can take the original equation, rewrite it with changes. Q1 stays the same. Q2 stays the same. R is now doubled. Pull out the change, and boom, it's 1/2 the original. It's nice. There's no squared on the bottom. You will accidentally put a squared on the bottom at some point. How do I know that? I have put a squared on the bottom at some point. It will happen to you if you solve enough problems. Be careful. When you are creating that squared or adding that squared is one of the most classic mistakes. Be careful. Double check your work on these kind of things. Yay, great job. Cool. All right, The next slide I'm about to show you is going to look all sorts of crazy. The equation is going to look crazy. I mention it because it's like the mathematical way of doing this, but I'm going to kind of talk you through how I do it that's a little bit easier to understand. So the next slide is about what if I have more than 2 charges? What if I want to find the energy stored if there's more than 2? So before I even show you the slide, I'm going to tell you the technique that I'm going to use. We're going to build the system. We're going to build the system. We're going to find the energy required, the work required to bring 1 charge in. Then we'll find the work required to bring a 2nd charge, then a 3rd charge, then a 4th charge, and then we're going to add that all together, and that's the energy stored in my system. So, that is represented by this. That is exactly what this is doing. Again, I'm not actually going to use this as a double sum. This does work, but I think it's kind of trickier to explain when we use this. It can kind of be tricky to see. But what you are doing here is you're finding the energy to add each charge, and you're building the system. Cool. I'm going to show you all how to do it again the way that I think is a little bit more intuitive. I'm not going to give you all a system with like 10 charges because, oh my gosh, it'd be so unpleasant. So let's just do the next step. I have 2 charges, both positive. I start with 2 charges. What happens to the energy of my system if I bring in a 3rd charge? And so here's a technique I'm going to tell you all. Find the energy, find the work required, find the change in potential to add 1 charge. Then find the energy required to bring a 2nd charge in. Then find the energy required to bring that 3rd charge in. We're building our system. We're like, bring 1 charge, then another, then another. And then add all of this up. Energy to bring 1 charge in, energy to bring a 2nd charge in, energy to bring the 3rd charge in. Then add all those energies together, and that's the energy stored in your system. So you have key here. First charge is 7 charges. Third charge is 5. Yeah. So, how much energy did you bring first one in? So is it fighting anything? If you bring up 1 charge, is there any other charges that's happening behind against it? There's 4. There's nothing else there right now. It's empty and void, and we get each of these charges next to it. If you have 1 charge, 0. 1 charge. There's no energy stored in 1 charge. To bring the 2nd charge in, how much energy plus? What was the energy required? Now we got 1 charge sitting there. What's the energy required to bring another one far away?
Yeah, but I'm trying.
In this case, where X would be, it actually would turn positive.
You have 1 charge.
I can bring the 3rd charge. That 3rd charge consumes both of the energy. So it's having to find each one in. Then you add up everything. Thank you. Yeah. How much is the energy to bring 1 charge?
Yeah, they are.
Not
If I bring in the third,
that would be a second charge.
I don't understand what you mean.
Bring one.
I mean, like bring in a charge.
Now we're bringing a second charge. One charge is
So what about what's the energy change you start with zero? Nothing else. Then for the second time, you got the second charge. Then it's the one that we just did before.
now we're going back to third charge. It's 5
When you add that third charge,
So that's the 5 1.
you have to calculate for one, the first one. Exactly. All the equations together. First one's zero, so first one out of that you are like sum them all together.
Okay, so you're adding 1 on 2.
Yeah, or like, do you want
Pretty much.
Okay.
All right, I'll give you all like 10, 20 more
I don't
seconds.
know, what's the answer though? Nothing. Yes, okay. Then on 1 on 2,
You're not allowed to.
that's something. And then you're adding 3 and 1.
No, you are. It has to be. I know. I'm saying I like typing on this one. Just because I think it's easier to search. But neither of these have that. When you do moments,
Oh, I mean for this. Everybody has another one. This next one is like 3 charges.
All right. So I'll leave this. I'll close it out in 5, 4, 3, 2, 1. Boop. So we're building our system here. We're storing up more and more energy as we add more charges. How much energy is required to bring one charge from infinitely far away to a place where nothing else exists? 0 energy is required to make that happen. You're not fighting against anything to make that happen. Nothing else is there. So the energy stored in a single charge by itself with nothing around it is 0. A single charge has no energy stored in it. It's not going to do anything if you let go of it. It's just going to exist. Now, I bring a second charge in from infinitely far away. I bring it on in. And we just did that problem. How much energy is stored if I bring a charge from infinitely far away? K, Q1, Q2 over R. In this case, all the Q's are the same. Q, Q over R. Cool. Now I got 2 charges there. Now I'm going to bring a third charge in from infinitely far away. Doesn't matter the path it takes, which is kind of cool. This is called a conservative field. That's why. Won't get too much into that. I bring this third charge in. This third charge now sees the other 2, and it has to fight this one, and it has to fight this one. It is having to fight both of them. So how much energy is stored from fighting this one? K, Q, Q over R. How much energy is gotten from fighting this one? K, Q, Q over R. So what's my total energy? I got 3 of these things. My total energy stored is 3. Well, here, let's just write it out. Equals U1, the energy to bring U1 in, the energy to bring the second charge in, plus the energy to bring the third charge in. 0 plus KQQ. Look, I'm just going to write Q squared over R at this point. Plus KQ over R, Q squared over R, plus KQ squared over R. Long story short, this is 3 times the energy stored with just 2 charges. If I added a 4th charge, that would add an additional 3K cubed squared over R to this term. Because it'd have to fight 3 charges. If I could somehow bring it the same distance away, R, make like a nice equilateral triangle. Okay, what's the point of this? Why do we go through this exercise? Let me connect it to something that you all experience every day. I'm pretty sure everyone experiences every day. Charging your phone. When does your phone charge the quickest? When it has a lot of battery or not much at all? If your phone, when it has 0 battery to it, charges really quick. Why? There's no charges that it's having to fight. As you charge your phone, you are literally moving ions over to one side of the battery. And to keep doing that, you're having to fight all those ions that you added before. So what ends up happening is as time goes on, your phone charges slower and slower the closer you get to 100%. Because it's harder and harder to bring more charges over to that side of the battery. The first charge is easy. Everyone after that gets harder and harder and harder and harder and harder. This is going to relate to capacitors as well. Capacitors charge super quickly in the beginning, and then they kind of peter out. Another example of this is like, let's say like inflating a car tire. The first part's going to be easy because there's not many air molecules inside it fighting against you, but as time goes on, you're having to push against this filled thing. And it gets harder and harder and harder. And you store more and more energy because of it. Because you're having to put more energy into it to make it happen, so you're able to store more because of it. All right. We are going to try this. Well, I say try this one. We're going to do this one. As crazy as this sounds, this is going to be the same process as we did in the first problem I gave you today. With a caveat. With a caveat to it. There's one extra step we're going to have to do. So let's read through this problem, then we'll actually solve it, and I'll try to convince you all that it's very similar to the water balloon dropping. An electron is released from rest at distance z above a positively charged infinite plane with charge density sigma. What is the speed of an electron just before it hits the surface? Use QE for the charge of an electron. All right, so what are we solving for? V. The velocity of this electron. We draw a pretty picture. I got my infinite plane, got a bunch of charge on it. Yay. We're going to say it's positive charge, so it actually attracts. And we got our electron chilling up there. And my question is, what is the speed of it right before it hits the surface? Okay, how are we going to solve this? Rule of thumb, if I ask you how fast something's going in this class, it's very likely you're going to use conservation of energy. That's just a good thing to kind of keep in mind. I haven't told you why yet, but trust me that that's going to kind of be a trend in this class until we get to magnetic fields. So, let's write conservation of energy. We're going to kind of work our way backwards to seeing if we can figure this, why conservation of energy is going to be useful. Energy initial plus kinetic energy, or potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Conservation of energy. Yeah, this will work for us. And we're going to ignore that work term because we're going to say the change in potential is causing the work. You kind of have to make a decision there. So let's rearrange. Well, actually, let's get rid of this. How fast is it moving to begin with? 0. That term goes away. Move the potential energy to the other side. So move the potential energy final to the left side. And I'm going to get potential energy initial minus potential energy final equals kinetic energy final. Okay? I'm going to do one more step for you. Do you all know what I can replace that ui minus uf with? It's something we've seen in previous slides. It's another way of writing it. This is the negative change in potential. If you're like, whoa, how's that the negative change in potential? Just pull out a negative sign, and then it's uf minus uf. Negative uf minus ui equals kef. Therefore, the negative change in potential equals kef. If only we had an equation for the change in potential in terms of things that we may or may not know. Try it out. I'm going to leave it there for y'all. Oh, and you're going to use QE for the charge of an electron and ME for the mass of the electron. You don't actually have to know these values. But you do, they will show up in your equation.
So do we use, what's his name? Gauss? Yeah, they gave us charge density. So E equals to to calculate the field of that infinite plane with the Gauss law.
No, because we're going to find electric field, right?
Okay.
With Gauss law. Then if you can move
Yeah, the only problem with using computers, we only know one.
right, yeah, no, I'm not saying.
No, if you pull
I'm saying we're going to make this find the electric field, right? With Gauss law, and then we'll need
This is equals. So 5 minus 2 is the same as negative 2 minus 5. No, you're good. That's good. It's a good question. Oh, look, it's gonna, yeah, that's what I can do. Yeah, it's easier with numbers sometimes.
Just so like,
What you're used to, but it's variables.
I guess you would say,
Right.
you would be
Y'all figured out
sigma
what
over, or sigma times the area.
Yeah.
Yeah, one over it's just like sigma over 2, that's
So
fine.
yeah, what is the negative
integral
Do
What is that expression?
you have it written down? Who else?
I do somewhere.
Okay. It's fine if it's like not easy.
What is this?
Once we know that, that's
Q times the integral. For Q is the charge.
Why are you getting,
And E is the electric field.
negative?
Find
I
the
thought
electric
that
field.
you wouldn't have a U final.
It's in the charge.
That's what's going on.
Oh.
Because it's normally when it hits the surface, it's
So we can just use that.
0.
So
If you're defining the surface, it's
Yeah.
0.
Nice.
Yeah, I think that's everyone's really
as well.
Wait, sigma over 2. Q is the charge. Charge and the E is the field decision.
Is equal to the electric field.
What electric field is it? There's the equation. 4 is right. 1, 2. Up to you. Yeah. At some point, it's good to derive it, but it can be whatever.
Just QER. Oh, we can't do that.
Why is it U final 0 for this one?
Yeah, we probably have to use that.
Like if you define the plan to be 0, your
E final. We don't need E final.
the U, the potential energy.
Oh, so we're gonna replace it with the integral.
Oh, okay. But I mean, like
It's
even-
not 0 because the electric field won't be 0.
Oh, okay.
The
Gotcha.
potential won't be 0.
Gotcha.
It'll be a fine. It's right before. It's This is so this problem is where the sound is the same as gravity.
Okay.
It's a just like gravity is a constant.
Are you just calculating the work with the integral of like the force over the distance? Okay.
All right, to give you all the next step, realizing that the negative change of potential has shown up in a previous slide. The negative change of potential equals If you had two charges, cool, we could use this. Oh, we don't. But we have a charge in something making a field. The big old infinite plane of charge is making a field. So, and the negatives will cancel out. So to kind of write this out, again, I'm just going to show you the next step. So this means, so negative change in potential energy equals the integral Q times the integral of E dot D dL. Like there's so many things I could put here. Let's go with dr. It doesn't, you're going to have something else anyway, but I don't want to give it away. So, here's my charge. What's making the electric field that the charge is in? The infinite plane. Do you know the equation for the electric field due to an infinite plane? And or could you derive it? Chuck it on in there, and then integrate over the direction it's traveling, the dot product within the field. Just E, dr cosine theta.
That would be Q or
Oh, it's distance Z.
Oh. This. Oh, it's D.
Under Z F.
Wait, the potential energy plus.
What is it?
Then
So this all good?
So all it is
This is
yeah, but that's
wait, it's the Q, right? This is the change.
no. Oh, yeah, you're right.
The charge times the field that's in dot with the package. So Q here would be. Wait, I think it's just DC. It's fine. I don't know
There's like clearly like
okay, Z is vertical. So the negative is Z.
Oh, so you're saying this
yeah.
Yeah, it doesn't matter.
And then it's a constant.
What's the equation?
So all that I do is separate.
Oh, yeah, I guess it
There's an equation for the electric field.
All right, to keep the ball rolling, does anyone remember the electric field due to an infinite plane? You derive it from Gauss's law, or you Googled it right now. Either way is fine. Did anyone find it? It's a really nice equation. Sigma over 2 epsilon naught. That's the equation for the electric field due to an infinite plane. That came, we did that from Gauss's law. We did a cylinder through it. It's one of the problems on the problem set. It's good to kind of go through. What's really cool about this is it's all a constant. Sigma, it's constant. 2, it's constant. Epsilon naught, it's a constant. Chuck it into your integral. Now there is kind of one thing I'm not too worried about in this case. Yeah, this is fine. So I'm going to give you all kind of a heads up on this. That dot product, if you all remember that dot product, a dot product between two things is the same as the magnitude of A times the magnitude of B times cosine of the angle between them. Which way does the field point in this problem? Up. Which way is my object going to move? Down. So what's the angle going to be between them? 180. That is going to spit out a -1, but the charge of an electron is negative, so it'll kind of cancel out. The negatives will cancel. That's what I want to let you all know. So chuck this in. You all need to replace dr with actually the direction it's moving. Is it moving up, down, left, right, in, out? What variable might we want to use for up, down? Pick your poison. Replace it with that. Pick your bounds. Where am I going from and to? Try it out. Yeah, just make sure you have the order. Final minus initial. So final will go, actually, if you want to do 0 to y, you'll start at y and actually go to 0. So your initial will be y and your final will be 0. Because it starts at y and it ends at the plane.
Like this is the right.
Yeah, in this case, it's just z to 0.
Initial.
Z to 0. Yeah, or
I just want to say.
you can do that. In this case, I'd say this is z, so you might put dz instead. It doesn't matter. The dy would work totally fine as well. You would just still do 0 to z, or z to 0.
Oh, that's just conservation.
You gotta do stuff.
The energy start with the energy.
You gotta try to do some initial.
So I kind of just said,
And I would do it now.
no, I mean my schedule. What they have for their that's just definitions. Now, negative change potential equals that. The negative part should go right now. So that's what I got. The definition of electricity.
Call it today.
So this are vectors, that's the electric field in the plane. That goes where E is. So this, I'm gonna go ahead and start solving this through. I think so I'm gonna start solving this out, the last little steps of it. So y'all can see all the pieces together. And actually, I mentioned that negative. Turns out that negative was important. It does cancel out, but in a way that you might or may not have realized. All right, so let's keep chugging along. So again, I'm going to write out every step here. Integral of E dot. Now, I will say, instead of dr, what might we switch to? What direction are we moving? X, Y, Z? We're going to use Z. The only reason I said Z over Y, if you used Y, that's fine. The only reason I use Z is I said it starts at a height of Z. So just to kind of like be consistent there. If you chose dy, it's perfectly fine. It will change nothing. It helps kind of with some clarity because I chose Z here. If you chose dy, it changes nothing about the answer. Now, what are the bounds of my integral? Where do I start and where do I end? Where does my negative charge start in this picture? It starts at a height of z. Where does it end at? A height of 0. Just plug it in the pieces, building the integral. And if you want, you can put the equation for kinetic energy here as well. Cool. Now we're going to substitute the electric field due to a point. We're going to actually do a couple things here. We're going to write this as Q integral of E, absolute value of E, absolute value of dz, times cosine of the angle between them. This negative sign is going to end up being useful. What did we say the angle between these was? 180. Why does that matter? It's going to give us a negative sign. That negative sign is going to be helpful later. So that's going to spit out a negative sign. And then I'm also going to take this electric field and chuck it in here. sigma over 2 epsilon naught dz. Now, this should be one of the easiest integrals you ever do because everything is a constant, so it all gets pulled out. So that means it's negative q sigma over 2 epsilon naught dz from z to 0. And you can see, maybe now you can see how this negative sign is useful. The negative signs are going to cancel. Just to write out all the steps so you can see those negative signs canceling. So that turns into negative q sigma over 2 epsilon naught times 0 minus z. Negative signs cancel. And if you just rearrange, so then I'll write out this, q sigma z over 2 epsilon naught equals 1/2 mv final squared. The 1/2s cancel. And vf equals q sigma z over epsilon naught m. And that's the answer. Square root. Thank you. Boom. All right. What do you take away from this problem? What do you take away from this? If there is a change, so if you want to figure out how fast something is going, you can do this integral, find the work done, like in this case, negative change of potential is kind of like the same as the work, and you find the velocity. As weird as this sounds, this problem was just like the one we did at the beginning of class. You're like, how the heck was this the same? The part that was different was having to do this integral. The part that was different was having to do this integral. You can imagine this whole nonsense term here, though, is just the gravitation, is just 9.8. This is kind of like gravitational constant. This is kind of like my height. G times h equals 1/2 v squared. Height times a number equals 1/2 mv squared. What did we do at the very beginning of class? Height times a number equals 1/2 mv squared. So it's the same type of problem, it's just a different force that's caused.